Hello and welcome to this bubble cell animation simulation tutorial. What we've got here is a bunch of bubbles created in geometry nodes and simulated using some distance constraints that are also present in my cloth simulation video. And then we have this one bubble that is attracted to this empty object, and then we animate the empty so that this one controlled bubble sort of goes in between all the other ones, pushing them to the side and eventually exiting the bottom with some nice simulated bubble pressure animations that come out of the sim itself. The blend file for this tutorial is available through a link in the description, so check that out if you'd like, and without further ado, let's get into it. Okay, so here are all our nodes. Before we go into all the details, we'll just do a quick overview. The first thing we're going to do is initialize the bubbles. What that's going to do is create all of these bubble objects and set up the constraints between them for the cloth pressure simulation. Then we're going to enter our simulation loop. We're going to set the rest center attribute of the controlled bubble based off of this empty object. So this is the controlled bubble up here, which we'll talk about setting up an initialization, and the empty is where it sort of tries to go. And so that's how we control our animation. And so we set the rest center by the empty on the set of the bubbles geometry, which is marked as controlled, so just that controlled bubble is marked that way. And then we set the rest position, which is slightly different from the rest center, because the rest center is the position of the empty, but the rest position is on every single point. So we want to make sure that each point is not just going to where the empty location is, because we wouldn't have a bubble, we just have a lot of points in the same location. So instead, we store a rest position, which is based off of the rest center plus the rest offset, which is initialized within the initialized bubbles node group. So we just add the rest center to the rest offset. That gets our new rest position for the control node group. And then we go into our simulation steps. We've got two of those here. So this simulates all the cloth simulations, and then it also, on every single point, brings the points towards their rest position, which is always based off of their rest center plus their rest offset. The last step in our simulation is the propagation of the material. So as you can see in the rendered version of our animation, let me actually turn on this solidify modifier that I had turned off. You have the bubbles, which are shaded like bubbles, and then you have this white sphere, which is the controlled sphere. So it has an attribute called material, which it only has, but when we're doing the collisions between the bubbles, if one of the bubbles is colliding with this one, then with the geometry that is marked as controlled, then its material attribute is inherited and then sort of propagated across the bubble over time. You can kind of see how the color starts where it touches this controlled bubble on this bubble over here and then fades into the rest of the bubble. You can see that more clearly maybe on this one over time. So the propagation of the material attribute among the different points on each bubble happens in this node group. Then we're done with our simulation loop. We simply set the geometry as smooth shaded, set the material to sphere material, and that uses the material attribute in order to change the shading of the rendered bubbles. And that is all we have for the overview of the whole node group. So the next thing we'll do is jump into this initialize bubbles node group. What this node group does is it initializes the bubbles in two different cases. One for the controlled bubble, so these four nodes up here are what define the point that ends up becoming the controlled bubble. And then what these nodes do here is the second part, which is define all of the points, which are the centers of the bubbles in the main bubble group. So what we're really doing here is we're just setting a couple of attributes that are going to be used later on in the network on the points that will be used as the centers for the icosphere instances, and the icosphere is what becomes the bubble mesh. So the way that works is for the controlled bubble, we're just making a single point. We're setting it to this position, which is just, up here. And then we're storing a material attribute, which is set to 1, because we want this to be the only bubble with the material attribute set to 1, because in the shader, if it's 0, it just controls an interpolation between two different materials. In this case, this sort of bubble material and this more shaded material that can be a color depending on which bubble it is. And that's what controls that. So this material sets at 1. The material attribute for all the other bubbles defaults to 0. Then we set the controlled attribute to true. That's only true for the controlled bubble. And then also we'll set the bubble size to 0.25. And that's just something that we chose because we wanted the bubble to be that big. And the rest of the bubbles have a similar process, except for we need more than one point. So what we do is we create a grid, and then we distribute the points on the faces of that grid. We're setting that to Poisson disk, and here you can see the rest of the settings, but that's going to create a distribution of points, which you can see in a viewer node, and you can see how those are the centers of all the bubbles. And then we are setting the bubble size, which gets piped into the radius of the instances when we instantiate the icosphere. So we set that bubble size to 1/2 the distance between the current point and the closest point to it. So we use the index of nearest node to find the index of the nearest point to the point that we're currently processing. Then we're using the sample index node on the same geometry with that index of nearest node piped into the index to get the position of the closest point to the point that we're operating on. We just get the distance between those two positions and we divide that by 2. And that's just so the bubbles get initialized at a size where they'll kind of fit with each other. So if we take that viewer node and we just move it over to this instance on points, what you can see is that none of these bubbles intersect with each other at the start, and that's because they're looking at the closest point and making their radius, or the scale of the actual bubble, just 1/2 the distance between each of these points. And what's a little confusing to me right now is I'm seeing like this bubble. Why is this bubble not touching another bubble? They should all touch. Oh no, this actually does make sense. Forgive me. Because, does this make sense? It should make sense. It's finding the closest point, and so in some of these, the bubbles are going to end up just touching each other. It should be like pretty perfect. But on others, this one for instance, the closest point to this one is not this point. So this one is halfway between these 2 points, but this one is halfway between these 2 points, and then this one must be halfway between these 2 points, which means that this is halfway between these two, but this one is halfway between these two. Okay, so that sort of propagates, but the same principle applies in that none of the bubbles are actually intersecting with each other. At most, they're just barely touching the edge of the closest point center, closest bubble center to the given bubble center. All right, at length, we'll just continue. Sorry for the rant. So we instance these icospheres on all of the points that we set up for both the control and the main bubbles. And so that's just an icosphere mesh primitive with a radius of 1, subdivision set to 4. We take the bubble size named attribute and input that into the scale, so that just applies to each of the 3 fields of the scale vector. And that's where we're at. Next, we're going to store a couple of attributes on the instances before we realize the instances, because we want to get data about the index that will then get mapped onto all the individual geometric primitives of the bubble mesh after the realized instances node. So these two things are bubble index, so that's just the index of the instance. We're just storing that. Make sure to set this drop down to instance, so which domain to store the data in. and that'll just get transferred again upon realized instances. And we'll do the same thing for rest center, and that's just the position of the instance. So then we realize the instances, and we're going to store a couple of other attributes, namely the rest position attribute. So this is just the position of the points now. Later on, we could recreate this from the rest center plus the rest offset, which here is really just defined as the position. So that's just the same as the rest position in this case, minus the rest center attribute, which we defined here. But we're storing the rest position explicitly because we are, and it might not be the perfect thing, but it works, and that's good enough for us. Next, we're going to go into the store neighbors node group, which stores all of the indices for each of, here, I'm going to turn off this solidify again. So let's actually turn on the wireframe mode. So what we're doing is we're taking each point, which has an index, which is just a number like 0, 1, 2, etc. And then we're getting each of the edges for each point. In this case, we're actually just doing them up to 6, because on an icosphere, they might have 5 or 6 neighbors, but no more than 6. So we're doing up to that point, and then if there's a neighbor that doesn't exist, let's say we've got a point like down here has only 1, 2, 3, 4, 5 edges connected to it, so only has 5 neighbors, and the 6th neighbor is just stored as an index of -1, so we know it doesn't actually exist. But for the ones that have 6 neighbors, all of those are going to be filled with an index of each of the neighboring points or neighboring vertices. And then we also store a neighbor distance attribute, which is just the distance between the point and the given neighbor at the beginning of the simulation. So right here, this distance, whatever that is, that's sort of the target distance between these 2 points. And then during the simulation, these particles move based off of a velocity and whatever other forces we want to add to them. But then there's a step where they look at all their neighbors, and then they find a offset vector that brings them closer to each given neighbor, such that they will be the distance, the same distance that they were at the beginning of the simulation. So they always try to sort of find that position, and it's got 6 neighbors or 5 neighbors. And so what we do is we find those correction vectors, and then we average them to get the actual correction vector that we apply to any given point. And over time, that's what creates a cloth simulation, along with a number of other forces. In this case, we're using a pressure force, which is just a force that points outwards away from the surface for each point, so along its surface normal, which is just a vector that points away from the surface of the mesh. And that's what we need to use this store neighbor attributes node group for, is to identify and then record the indices of the neighbors for each point. So jumping into that, we see that we have 6 different node groups, and what these do is each of them stores one neighbor. We have neighbor 0, neighbor 1, neighbor 2, neighbor 3, neighbor 4, neighbor 5, and that's actually a total of 6 because we start at 0. And the name of the neighbor is dependent on the edge index, or maps onto the edge index. So these are the inputs for each of these node groups, and we can just look at one of these and we'll know what happens in all of them. So we'll hop in here and we will look at how we get one of those individual neighbors. So what we're really doing is we're finding the edges of the vertex, and we're finding one of those edges. So that's based off of this sort index input, which is connected to the edge index input of the store neighbor of edge node group. So for the first neighbor, it's the edge index is 0, then 1, then 2, etc. And so that's how we select the individual edge that we're going to store the neighbor for. So let's say this is the first edge of this vertex or this point. So now we have identified the index of this edge within the geometry. And what that allows us to do is sample the edge using the sample index node and get some different information about it. The 2 pieces of information that we're getting are the indices of the 2 vertices connected to that edge. So in that case, that's going to be the vertex of, or the index of the current vertex, and also the index of the neighbor. The reason we do that is we don't actually know which one of these is the neighbor versus the current one, and so we need to create a test to figure that out. And the way that we do that is we test whether or not the sampled index of each of these is equal to the index of the current point that we're dealing with. And really we know that one of them is the neighbor and one of them is the current index, so we just do one of these tests. So we're saying, okay, so if the vertex at index, or the first vertex connected to this edge is equal to the index of the vertex that we're trying to find a neighbor for, then we're going to use a switch node to say, well, if it's equal, then we actually want it to be, we want to draw the neighbor index from the vertex index 2 because we want it to not be equal. And then if it's false, we'll take the index from vertex index 1 by sampling the edge as we have. And then we'll also say that if, remember how some of these vertices have 5 neighbors and some have 6. I think most have 6, definitely, and only some have 5. So we need to actually store an index of -1 for the neighbor if we're dealing with an edge index that is actually greater than the total number of edges connected to that vertex. So we're using this total output of the edges of vertex node, and we're just comparing that with the edge index input. And so if the edge index input is greater than or equal to the total number of edges, we're going to set the neighbor index to -1, signifying that there is no neighbor at that neighbor index. So that'll apply in this case only to cases where we're actually in this neighbor 5, which will be the 6th neighbor because we start at 0. So hopping back in there, we actually store that named attribute, and that's based off of, or the name of that attribute is based off of the input that we have at the node group level. So in this case, that's neighbor 5. And then we also store the distance, or the target distance, between the neighbor and the current vertex. And we get the name for that by joining the input string, so neighbor 5 or neighbor underscore n, whatever the number is of the index that we've decided, and then we just join that with dist, that signifies distance. And the delimiter, or just the character or characters that we put in between the joined strings, is just an underscore. So we'll get neighbor underscore 5 underscore dist for the distance attribute. And the way we get that is we have to sample the position of the geometry at the neighbor index. So that's either going to be -1 if the neighbor doesn't exist, or it's going to be the index of the edge that we're dealing with currently that is not the index of the current vertex. And so we're just sampling the position of that neighbor index, and then we're just using the distance node with the position of the current vertex position. And then we're also setting that to 0 if the same condition for whether or not the neighbor exists or not is met. So if the neighbor doesn't exist, we just set the neighbor just to 0 in the same way that we set the neighbor index to -1 if the neighbor doesn't exist. Otherwise, it's the distance between this sampled position that we just talked about and the position of the current vertex, and we store that in an attribute, and that's how you get all the information you need for the distance constraint in the class simulation. And with that, I believe that we have finished the initialization of the bubbles. Wonderful. So moving on to the simulation loop, we've got the block defined by the simulation input and output, and then we're going to set some attributes for the controlled bubble each frame. And all we're doing is we're setting the rest center and the rest position. The rest position is what's really important because in each of these steps, there is a point at which we move all of the points towards their rest position. And so that's what we really need. And we set that by first setting the rest center, which is just going to be the position or the location of the empty object. And we're only setting that for points on the entire bubble geometry that are marked as controlled with a Boolean attribute that we set only for the controlled bubble up here within the initialization. And so we set the rest center if it is controlled, so only for these points, and that is set to the location of the empty object. And then we update the rest position attribute using the new rest center attribute and the rest offset that we also stored during initialization. So you just add the rest offset to the rest center. Now you've got your new rest position, and that results in the bubble, or the controlled bubble, following this empty over the course of the simulation. Then we will move on to the two simulation steps. And so here is again where we perform the cloth simulation, which has some pressure applied to it, and we're also moving all of the points towards their rest position, which just acts as another force in the simulation. So going from the beginning and doing a brief overview, if you've watched some of my other videos, this is a pretty common technique related to something called position-based dynamics. But what you do is you store the last position, or the position of each point, at the beginning of the simulation step. Then you make some changes to the position of those particles, and then at the end of the simulation step you update the velocity, which is just the difference between the current position of the point or particle or vertex in question and its last position that you stored at the beginning of the step. So just the difference between the position at the beginning and the ending of the simulation step. So you just subtract those. In this case, we're scaling by 0.9 to make them slow down just a little bit. You don't technically have to do that, but you can. And then you store that in the velocity vector attribute, which is used as a force or a change to the position of each particle during the simulation step, directly after storing the last position. So we store the last position, and then we add the velocity to the position of each point. So that's really just setting the position with the velocity attribute piped into the offset input. And then we are moving all the particles towards their rest position. This could be a node group 2, so why don't I just do that? I'll select all those, press G tab to go out, and then I'll just click in here to rename. Move towards rest position. And so now we've got that in there. So again, all this does is it gets the rest position attribute. It subtracts the current position of the particle from the rest position, so that just gets a vector that points from the position of the current point towards the rest position. Then we're scaling that by a small value, so 0.005, and that'll just control how quickly each of the points moves towards its rest position. And then we just use the set position node to actually change the position of the particle, and again we're using the offset input. So after we move towards the rest position, we're going to apply pressure. We have a scale input here, so that's also just controlling the amount of pressure input that we get during each simulation step, and that's really just going to be the normal of the particle in question. So the normal, again, is just a vector pointing from the point away from the surface of the mesh. So just scale that by a small amount and just move it out, so then each frame the bubble is kind of pushing its points out and kind of trying to stretch, but then the distance constraints are pulling it back together, so there's a little bit of a push and pull there. So after we apply the pressure, we apply the constraints, and so that's the pull that we were just talking about. And within the apply constraints node group, looks pretty simple, but there's a little bit more in this node group. So we're setting the position based off of the average distance constraint correction vector. So we get that average correction vector through the get average distance constraint correction vector node group. And if you've watched my claw simulation video, you'll see something similar to this in there. So what we do is for each of the neighbors, we're getting the distance constraint correction vector, and then we're just averaging them. And so the way we do that is we add up all the correction vectors, and we're also adding up whether the neighbor exists or not, so that we get the total number of existing neighbors that we use to divide the resulting correction vector sum from, or you just divide the correction vector sum by the total number of existing neighbors, and that gives you the average correction vector. So if we jump into the get distance, the get average distance constraint correction vector node group, the way that this one works is we've got the neighbor name, and we're recreating the neighbor distance attribute name in the same way that we stored it in the initialization node group. And then we're getting the position of the neighbor with the sample index node using the attribute that stores the index of the neighbor that we get from the neighbor name. And then we subtract the neighbor position from the current particle position, and then normalize that so that we get a vector of length 1 that points in the direction from the position of the current particle towards the neighbor particle. And then we're scaling that by the amount that you'd need to move the current particle position to be the original distance from the neighbor. So you're moving towards the neighbor such that you satisfy the condition that you are the distance from that neighbor that you were at the beginning of the simulation. And the way we do that is we first get the distance between the current particle or current point position and the neighbor position, and then we subtract the neighbor distance or the target distance from that distance. So if you subtract that, you'll get the difference between the current distance and the target distance, and that's the amount we need to scale the direction vector from the current particle position to the neighbor particle position in order to put it in the correct position, or the position that satisfies the distance constraint. And so then we also have an additional scale vector math node right here that just basically makes this vector 0, 0, 0 if the neighbor doesn't actually exist. So if the neighbor index does not equal -1, then the scale is 1 because this result is true. But if that's false, so if it does equal -1, then the result is 0. We scale this vector by 0, and if you scale any vector by 0, you get a vector that's 0, 0, 0, and that nullifies it from the correction vector sum that then we want to average. And so then we also output this same result output into the neighbor exists output of the node group. So this is really testing whether the neighbor exists or not. And then we use that. We're just thinking of this Boolean as a 0 or a 1, and it gets treated that way within these math nodes. And so we just add all of those up. And so what that does is we get the total count of all the existing neighbors, like we said before, and then we get the sum of all the correction vectors. And then we just scale that sum by 1 divided by the total number of existing neighbors. And that gives us the average correction vector that then we apply as an offset to each point in the simulation. And that helps us over a series of iterations, over a series of simulation steps, sort of try and satisfy those distance constraints, which is what causes us to have this nice bubble claw simulation, which is really fun. But it is considerably less fun without collisions between the different bubbles. So we handle the collisions within this collide others node group. And the way that this works conceptually is it does a raycast for each point, and it does it in the direction which is the negative normal, so inwards, away from the outwards facing normal. So if this is the point on this bubble, then we're doing a raycast in this way, and if it hits something else, if it hits a piece of geometry that doesn't have the same bubble index as the point that we're interested in. So we don't want bubbles to collide with themselves in this simulation, just with other bubbles. So that's going to be one of the conditions for our collision. So if this bubble, for instance, expands and then it intersects with this one, this raycast is going to look inwards towards itself, and it's going to collide with something that has a different bubble index, and then it's going to say, okay, well, I need to move a certain amount in the direction of, well, the opposite direction of the raycast, which is just the normal of the point that we have. And so it does that a little bit each simulation step, and if you tune the values in a reasonable way, then you get some fairly nice looking collisions, as we have here, that are actually like pretty stable also, which is nice. So the way that works in this node group is we have this raycast node. And so we've got the input geometry, which is just all the bubbles. And then we're looking to get the bubble index attribute, which we set during initialization. That was based off of the instance before we did the realized instance node. So the source position of the raycast is just the position of the current vertex minus a tiny bit of the normal, or a tiny bit of the normal scaled by -1, so -0.001. And that's just so the raycast, it's not colliding with itself, essentially. You need to move it a little bit away, or else it'll just collide with itself. And so that's the source position. And then the ray direction is just the negative normal. And then the ray length is just 1/2 the bubble size. So we don't want the raycast to go, you know, like through the bubble all the way over here, because this bubble is not colliding with this surface point. So we just want it to go in a certain amount, and I found that 1/2 the bubble size is pretty good ray length, and so that's what we're using. So after we do that raycast, then we have some information about the hit. We know if it is a hit, which we're going to use. We also know the value of the bubble index of the hit, so we use that to test, like, if the bubble index of the current point is not equal to the bubble index of the hit point, and there was actually a collision in the raycast, so something did intersect in the direction from the source position within the distance defined by ray length. Then, well, we also have one more. So I'm also testing whether or not the normal of the collision geometry, or the collision surface, is a certain amount in line with the normal of the current point. So the way you do that is the dot product. And if that's less than 0, then we're going to set the position. And so for the dot product, when the dot product is less than 0, you can kind of think, so you can think of the dot product, if you take two vectors and you project one onto the other. So if you've got like this vector and you've got this vector, and then you project this one onto this one, so it's just making this, so you just projecting just puts it right here. So that's you get this vector, and so it's not rotated because this vector is slightly shorter than this one. It's if you just project it onto this one. The dot product is the length, is this length that you get. It's the length of the projected vector onto the vector that you projected it on. And so if those vectors are normalized, then it's going to be like if they both have a length of 1, then, well, it doesn't actually matter if they're normalized or not. If this length is positive, then they're generally pointing in the same direction. If it's 0, they are orthogonal or perpendicular to each other. And if it's negative, then it's like this vector that's pointed, you know, away from this like whole swath of a hemicircular direction, if you project that on here, then this dot product is going to be negative. That all just to say, if the dot product of the normal and the hit normal is less than 0, then they are pointed in like mostly different directions. And that's just one of the tests that I added in when I was doing this. I actually don't know if it's completely necessary. Let's try taking it out. So let's just instead pipe this in here. Let's just see what happens. Well, it looks like it's not really, it's not really necessary. No, you know what? It's helpful. It makes it a little bit nicer. You see some of those little issues that are happening, like right there. Look at that weird glitchiness. So it's kind of nice to have that test just like, okay, are these surfaces really opposing each other? Because I guess when you kind of get in this situation where all these are smushed together, you can kind of get some false positives, and it's nice to weed out some of the areas that shouldn't actually be colliding. So if we reconnect that and run the sim again, I'm really not seeing any of those artifacts. So my intuition was correct. This was a good thing to use, and the result is quite nice. Thanks for bearing with my long ranty explanation of dot products, which I'm not sure is 100% correct, but may be helpful. You may learn something, have fun, etc. We'll repeat that at the end of the video. Okay, so if all those conditions are met, then we correct the position of the current particle based off of the collision. And so the way that works is we're taking the normal of the current particle, so we're always going to move in the direction of the normal to correct for one of these collisions, and we're scaling that by negative 0.6. So it's actually the negative direction scaled by 0.6. And 0.6 is also just a value that I found that worked pretty well. If you set it to -1, I believe it's a little bit less stable. It may work in this case with this animation, but I found when I was just moving the empty around, it didn't work so well. But this actually looks pretty nice. So maybe I'm just mistaken. But I kind of think that yeah, there's wiggling. They overcorrect. Yeah, you can see here. I'll turn off the camera so you can actually see this. Yeah, you'll see how it's jittery at the edge. If I set this to -0.6, no jittering, much cleaner. If I set it to -0.5, it's also fine, but I like -0.6, so that's what I set that to. Right after we collide with all the other bubbles, we have this series of nodes, which again could be put into a node group, and this is constraining the bubbles between some, you can think of them as like vertical glass plates or something. So you can see how the bubbles don't expand as much as they could in the both top and bottom directions, and that's because we just have a condition that sets them between between 0.4 and -0.4 in both the positive and negative z directions. And so we could set that smaller, like 0.1, and they'd be set in a much smaller two plates, but then that squishes them a lot, and you know, our collisions don't work as well. We could set it to 0.2, makes it a little bit better. 0.3 is also probably totally fine, but for us, we're going to set it to 0.4. And so this could be called constrain between planes or collide with plates, whatever name you want really. Let's just say constrain to planes. So we'll just put that into a node group again with Control G, just to make things a little bit cleaner. And if we hop in there, the way that works is it just takes the position of the current point, and then it essentially does a clamping operation using the minimum and maximum vector math nodes. And so we're setting x and y to these really, really large numbers because we don't want to be constrained on those axes at all. Z to 0.4. And then so for the minimum, we're just saying take the minimum of each component of the vector between the position and this one. So if the z component of the position is above 0.4, then we just set the z position to 0.4. Otherwise, the position remains the same. And then also for the maximum, it takes the maximum value. So we're scaling this combine xyz node by -1. So instead of it's negative 100,000, negative 100,000, and negative 0.4, and then we'll take the maximum value. So if the z component of the position is less than negative 0.4, then we set it to negative 0.4. And that's how you make sure that all of the points stay within those bounds. Then we've already gone over the update velocity node group, but again, you're really just subtracting the current position of the particle from the last position. We're going to scale by a small amount and setting the velocity attribute that we then use in the beginning of the loop to add the velocity. So that about does it for the simulation step. And then we've got this propagate material node group, which is outside of the 2 steps. So we're just multiplying these, or we're duplicating the step node group for just tuning the speed of the simulation. If you take one of those away, then they're just going to move a bit slower. So the responses of the bubbles isn't quite as quick. And you might even like that better than having them duplicated. But again, see, there's sometimes with these simulations, you've got to work with what you made and just build on top of that. So these aren't like unconditionally stable simulations. They're just pieces of art that we can work with to make something pretty. That's the beauty of being in 3D land, is we can be technically sophisticated, but we don't have to be, because at the end of the day, it's all about what you like looking at. Anyway, so we've got these 2-step node groups, and then we've got the propagate material node group. And what this does is it has this raycast material node group, which is really similar to the collision or the collide with other node groups. So it uses the raycast in the same way. So it's got the same ray length, it's got the same ray direction, and it's also got the same source position. But instead of looking for the bubble index attribute, we're looking for the controlled attribute. And if that attribute is true, so if the current point is colliding with the bubble that is controlled, so basically if any of these are colliding with a piece of geometry on the controlled bubble, then we set the material to 1. And so that immediately will set the material for, well, here, let's turn on that solidify modifier again so it renders correctly. So right here you can see how these points are starting to fade in. So this will make more sense if I explain the last part of the propagate material node group, which is you're just blurring that material, and you're also increasing it a little bit over time. So we just multiply by 1.05. We clamp that because we only want it to be a maximum value of 1. So take the material, multiply it by an amount slightly larger than 1, just so it raises over time, and then also blur that attribute so that it slowly propagates through all of the vertices that are connected by edges on a mesh. And so we just have that set to 3 iterations, a weight of 1. And so if you take away that blurring, what you're going to see over the course of the simulation is just the areas that touch this bubble. Their material gets changed, so you're going to see that trail kind of get left through the bubbles, but you don't get that propagation or that slow expansion through the rest of the bubble geometry that the controlled bubble touched. And so that's what these 4 nodes do. As we've just described, they just increase the amount of the material by a little bit, so that as you blur it, all the little values get bigger, and then the blurring keeps happening through the different steps of the simulation, and so the material attribute spreads and then it increases, and then if I hop out of the camera view, you can see that slowly over time they'll spread through the affected bubbles. Wonderful. Let's go ahead and delete the annotations. So I'll just delete that. And now we can go over some of the material settings. So we're done with the simulation loop after the propagate material node group. Then we're just going to set shade smooth because they're bubbles and bubbles are smooth. We don't want them to look like that. So set shade smooth, and then we set the material, which is going to be this sphere material, which we can then see in the shader editor. If I select the sphere material, one trick here is you can hit view frame all if you can't find where your nodes are. So the way this works is we take that material attribute and then we're just creating like a little bit of a float curve on it to control the rate at which it propagates through these materials. So it looks like I didn't hook that back up in the geometry node editor. Let me do that right now. Wait, I totally did. It's because it's cached. Okay, so if we go back to the shader editor, you don't really need to use this float curve, but I thought it looked a bit better. So if I take that out, you'll just see that the propagation just looks slightly different. I found that there was a little bit of a rough edge. I'm switching to, but I'm not really seeing that now. Anyway, I'll keep this the way that I tuned it, but full disclosure, not completely necessary. And that just gets piped into the factor input of this mix shader. And so the actual bubble material is just a super simple glass BSDF. I set the IR, the index of refraction, to 1.1. You can set to other things. 1.52, I believe, is glass or something. 1.45 is the default. I don't know. 1.1 just looks good, so that's what I set it to. But a really, really simple material there. And then we'll mix into this one, which is just a principled BSDF with the following settings for roughness, specular, subsurface, etc. Subsurface is set to 1. So this base color really doesn't matter. I'll set that just to default white so it's not confusing. And then what we're doing is we're taking a couple of the attributes. We always want the controlled bubble to be white, so we take this controlled, or gray actually, but with the lighting it looks white. So this is going to be 1 if it's controlled, 0 if it's any other bubble besides this one. So if controlled is greater than 0.5, then you'll use that as the factor to this mix color node, and that'll be this color, so I can set that to whatever, and the controlled bubble will be that. Otherwise, so all the other bubbles get colored this way. We take the rest center attribute, and then we're popping that into the coordinate vector input of a noise texture. So we've just scaled that to our liking. So let's run the simulation so we see all of the colored bubbles. So you can just set this to different scales based off of how much variation you want in the color and how quickly it changes over the center positions of each bubble. And then we're separating the color into its hue, saturation, and value components. And then we're using the hue component because we want the saturation and value to be the same. So we're just setting because if we don't do that, then you'll have a noise texture that just doesn't look the same. I mean, in this case, the value is way too high because of the way we've got all the lighting set up. So everything looks pretty much white with maybe some tints. And so you'd see also that here, I'll just pipe the saturation here. You'll see that the saturation is also not what we want it to be. We want it to be 1 in all cases. In this case, it's like between 0 and 1. So we just use the hue from the color we get from the noise texture set saturation to 1, value to 0.2, and then this color just sort of determines, you can use this to determine or to tweak the color of everything. So you can just move that around the color wheel. I'd keep it fully saturated for the purposes of this one. To get different sets of colors, Control Z that, because I just found this, which I liked. And so that's what controls the color of the bubbles. The last thing that we have to do is look into the lighting. And so the way the lighting works is you've got this gradient, which again is just something that I've tuned. Now the camera is an orthographic camera, and if I also hold Alt while I'm navigating around by holding down and dragging with the middle mouse button, if I hold Alt down, I'll snap into one of these views. You can press 5 on your numpad to switch between orthographic and perspective. So if I'm in an orthographic view, I'm only seeing one color along that gradient. In this case, it's this blue color. So if we switched to the world, so if we switch to the world material node group, then we can see what we're doing is we're taking the position of the point in the world, which is just a point on a big sphere. We're separating it into its separate XYZ components, and we're only using the Y component. We're multiplying and adding by 0.5, or multiplying by 0.5 and then adding 0.5 to get a black to white gradation from the bottom of the world to the top of the world. The reason why that doesn't look completely white is because in our rendering settings, well, maybe I'm wrong about that. Why does that not look completely white? I honestly don't know. It should. What the heck? Oh, am I looking in the wrong direction? Yeah, I guess it's white. It's just the filmic editing. Anyway, what that's going to do is allow you to create a color ramp that goes from 0 to 1. What did I do? This is weird to me. Let me check this right here. Color ramp. Oh. It doesn't look white because we've got the strength set to 25. So if I actually just pipe this in here, then you'd get this gradation. But it actually is white. It's just the color of the monitor. Just bear with me, guys. Okay, so multiply add to get a gradation between 0 at one pole to 1 at the other one, and then we're using a color ramp node, and this is where you get artistic. This will really control the lighting of the bubbles that are not affected by the controlled bubble, and they have the bubbles that have the glass material. So you'll see that if I move these, because they're refractive primarily, you're going to see the environment in the bubble. And so you want that to you want the environment to be something that the refractions on the glass material use in order to create something that looks nice. And this is one way that you can create an environment that'll make them look nice if you think this looks nice. So there you have it. That's it for the world material, and I don't think I have any other lights in the scene, so that's it for the lighting. And we've already gone over the materials, and I believe that that just about covers it. So I hope you enjoyed this tutorial. I hope you learned something, and above all, I hope you had fun. Until next time, bye.